So here's my plan as far as what I'm doing. I do intend to write up a practice exam for you. Hopefully, I will have that written by tomorrow. That's my goal. As far as talking about kind of just what to expect on your exam, I would encourage you all to look at the first test logistics. So if you're, let me go back to, so just so you can all see in Canvas in case you haven't looked. So here is your 16C Canvas. And if you scroll down to week 4 and you click on the week 4 summary, and it's a little bit hard to read. If you look here, it says, Friday, you're taking the first test. You can read all about the test right here. And then you can read about the test. And it's talking about the logistics, and there's kind of a lot to read there. As far as when it's going to start, I think you guys did a dry run of the assigned seating stuff today in class if you were there, but you will have an assigned seat in class. So she'll send that out, I think, on Friday, Thursday night, I guess. So look for that. Just show your work, calculators. There is partial credit, but you don't get points if you don't show your work. So you don't just write an answer, show work if it means sometimes there are things that are easy enough that you don't really need to show work for. But in general, you should default to showing work. What else do we have here? Study the best way to prepare is study the test. Study suggested problems in the weekly modules to make sure you know how to do all the homework problems. Okay, that's kind of a lot, but still, it's right. That's a great place to practice the homework problems. That's what I would say too as a teacher. I wouldn't necessarily expect that everyone did all the homework problems, but I would hope. And then if you have any questions, post them on CampusWire. Not particularly familiar with CampusWire, but okay. As you might be aware, Dr. Burke is not going to be in class on Wednesday or on Friday because she's going to a conference in DC. So you'll have someone, I think, Rohit on Wednesday, and then someone doesn't really matter who's, there's a word, I can't think of it, not monitoring your test. Proctoring, thank you. I was like, I know there's a word for this. There'll be someone proctoring, but it doesn't really matter who's proctoring your test, right? They're going to be there proctoring. But I think the most pertinent thing here is to note what your midterm covers. So at the very beginning, right, we've got sections 11.1 through 11.4, which is basically all the differential equation stuff. And then we have section 7.1 through 7.3, which is basically all the 3D graphing stuff we've done. Now, it seems like a very kind of minimalistic way of writing it down. Oh, sorry, you can't see what I'm writing. Seems like a very minimalistic way of writing it down, but that's kind of the gist, right? It's differential equations and the 3D graphing. Now, in that, there's a lot. Let's go back and talk about differential equations for a minute. So let me actually grab this other thing I have here. One sec. Your cursor, you're always hiding from me. There we go. Where'd you go? So yeah. So let's look at a couple of examples of differential equations. So there's, in my opinion, 2 or 3 types of things you might get asked about differential equations. One would be to, I could say even maybe, 2 or 3 things. So types of things you might get asked to do are to solve a differential equation. And it might be first order linear with an integrating factor, or it might be separable. You might get asked to show something's a solution. And I don't know, but I think you might get asked to identify some characteristics about a differential equation. Like, is it separable? Is it first order? Or is it second order? Or some other order? Or is it linear? I could see asking questions like that. I would ask questions like that. In fact, let me give you some examples of these. So, yeah. Let's look at a few examples of that third thing first. Let me give you the following. So let's say we have the following differential equation. Y prime plus 3y equal to 2. So right now, all I care about is this separable or not? Actually, is that right? Let me back that up. Sorry, that's actually the last. I really care, is this linear or not? So if I'm looking for linearity, I'm looking at the y's. So I'm really only looking at the y's that are not y primes. That y there raised to the first power is telling me, oh, this is linear. Whereas something like this, say we had y prime plus 3y squared equal to 2, is not. Because we have now a power of y that isn't just y to the first. Let's look at one more. What about y prime plus 3xy equal to 2? Linear or not linear? Yeah, thumbs up, linear. Because even though you have an x times y, it's still y to the first. Also, I would point out, this is the very kind of nice structure we are looking for in a first order linear differential equation. This is definitely linear. Then do I want to look at that one? Not really. Yeah. So let's look at, we're gonna actually look at all these again, but then we're gonna ask the question, what order are they? These are all kind of, sorry, these are not very exciting. These are all first order. They all have a first derivative. But if, for example, so I'll point out all of these are first order. On the other hand, we could write something like y double prime plus 3xy equal to 2. I like this question that I'm about to ask. What's the order here? Definitely second because we have a second derivative. But is this linear? It is still linear because as far as we're concerned, the y is only raised to a first power, right? The y double prime doesn't affect the linearity of this differential equation. So this is a second order, but still linear. But then I think the thing that actually really matters is separability or not. So some of these are separable, some of them aren't. We're only look at the first three here. So let's ask this first one. So is this equation separable? Well, I'm not sure. So what I'm going to do, I'm going to try to separate it. So I'm going to rewrite it as dy dx equal to 2 minus 3y. And then when I'm writing it that way, I have to ask myself, can I write the right-hand side as just things with x's times just things with y's? And the answer is definitely yes, because there aren't even any x's. So if you're missing one variable entirely, it's totally separable. So yes, this is separable. We could totally write it as 1 over 2 minus 3y dy equal to 1 times dx. And then integrate both sides. Not that we're trying to solve it, we're just trying to see that we could separate it into the y's on the left and the x's on the right. Question?
When you're going to separate it, you need to have 2 on the left side.
I do have, yes. So here's the thing. This is a really important thing about separable differential equations. If you're going to separate one side to the other, the only thing you're really allowed to do after you have dy dx equal to all the other stuff, once you get to here, all you're allowed to do is multiply and divide. You can't add or subtract. So the thing is, if I bring this dx over here, what I really have is dy equal to the whole entire quantity, 2 minus 3y times dx. And then once you're there, there's really no way to break apart the 2 and the 3y from each other. Yeah, excellent question. Glad you asked it. Let's look at the next one. How about y plus 3y squared equal to 2? Well, without even doing anything, the answer should be yes, for the same reasons as the first one. You can totally get, there aren't any x's, so it's definitely separable. Because there are no x's. Except for the dx's and the dy dx. Okay, the third one, y prime plus 3xy equal to 2, is more interesting. I don't think this is, but if I was going to try and check, here's the work I would do. I would rewrite this as dy dx instead of y prime, and I bring the 3xy over to the other side. So now the question I have to answer is, am I able to write the right-hand side as something with just x's and something with just y's? And the answer is definitely no. I can't do it. If I want to I can't factor out an x really, or if I do, I'm going to have a 2 over x minus 3y. That's not something with just x's times something with just y's. Similarly, if I tried to pull out the y, I'd be left with a 2 over y there. So this is definitely not separable. And I could see asking questions like this because they kind of test your understanding of the things. I could also see not asking them at all because they don't seem like they're getting it, you having to solve stuff. So let's look at another. Yeah. So before that, any questions about what we've done so far? Let me look here. So let's look at the following. So I want to show, so that's one type of question we could ask about differential equations. The other two things I think we could ask are to show something as a solution or to solve a different, I'm sure you'll be asked to solve a differential equation. The other thing I think you might be asked is to show that something like this, that y equal to x minus 5 over x squared is a solution to the differential equation x times y prime plus y equal to 2 times x. So here's how I would do this. I essentially want to find y prime, and whatever it is, substitute it in the place of y prime right there. And then similarly, so that I already have y, I'm going to take that y thing and plug it in right there after I've done the other part. So let's start off by finding y prime. So I'm going to re-express y as x minus 5 times x to the negative second, just to make it easier to differentiate. And then my y prime is going to be 1 minus 5 times minus 2 is plus 10 times x to the negative third. And then again, since I'm going to have to multiply stuff out, I would probably write this as y prime equal to 1 plus 10 over x cubed. And now I'm ready. I'm ready to plug this in here and that in there, and then see that I get the thing I'm supposed to get. So let's do it. So we're going to have x times y prime, which is 1 plus 10 over x cubed, plus y, which is x minus 5 over x squared. And here's what you actually shouldn't do. We shouldn't just say this equals 2x. We should actually do the algebraic manipulation to get to a place where we show that it's equal to 2x. So I'm going to multiply this out. I'm going to get x plus x times 10 over x cubed is 10 over x squared plus x. Feels like we're missing something here. Does feel like we're missing something. Did I miss it? No. Did I miss something? I don't think I did. I feel like I'm making a mistake somehow, though.
Is it the?
No, right? Because so let's write. So if we write it out, we can see that. I think. Yeah, that does. It feels like it's not going to work. That's not good. So this could happen. It's probably what happened. But what happened was somebody writing the problem that I was using. The real issue is I didn't check the problem before I did it because I thought it was written correctly. So this actually does, so I suppose here's what someone could have asked. They could say, show this isn't a solution. So if we do, if this is not a solution, just to not erase it all and do it again. We'll do a different one in a second here. Right when we get there, x times y prime, we're getting that. Yeah, definitely, this should have had like a 2 here or something. Interesting. So that's going to equal 2x, and then the 10 over x squared minus 5 over x squared is, oof. That is not equal to 2x. So this is not a solution to that differential equation. It happens sometimes. Yeah. So, looking for a second here. Yeah. Sometimes people write bad questions. So if something like this were to happen, just as an aside, like sometimes people make mistakes when they're writing things. It's just a fact of life. They don't mean to, but occasionally someone doesn't check a thing. And that's when it's very appropriate to ask a question in class. Like, hey, I'm doing this. I think I've done it right. I'm not getting this as a solution to the thing you said it is. Can you double check that it actually is? And depending on the class, some people will answer questions like that, some people won't. But it is not inappropriate to ask a question. Like if you think you've really done the work right, like I got here, I'm like, oh yeah, like this is not going to work out. That would be a perfectly fine time. And maybe you've made a mistake. I could have made a mistake here. I don't think I did. You guys don't, did we check, right? I took my derivatives correctly. That seems right. I plugged in here. Yeah. Let's look at a different example. One where things actually do work out. Again, sorry about that. So, yeah. Go back over here. Sorry, I've got all these problems here. Yeah. So let's do the following. Show that the differential equation sorry, the problem is I don't have one just teed up here for this next part. I'm like trying to find one. Sorry, one moment, please. Unfortunately, they're not super easy to make up. Give me a moment. Okay, well, here's a variation on this. Show that this differential equation, x squared times y double prime plus 2x times y prime minus 6y equal to 0 has a solution of the form y equal to k times x to the r, which is, again, a little bit different. I do think actually. So we're going to start in the same place. And our job here is going to be to find the k and the r that actually make this work. Okay, well, not too terrible. We're just going to have to plug in the y here, and then we're going to find y prime and y double prime, which aren't too terrible to find, right? The derivative of x to the r is going to be the derivative of k times x to the r is k times r times x to the r minus 1. And the derivative of that is going to be k times r minus 1 times x to the r minus 2. So again, when you're trying to show something's solution, you're just finding all the pieces you need to plug in. And then hopefully when you're plugging them in, things actually work out. So we're going to get x squared times k times r minus 1 times x to the r minus 2. Notably, when you multiply the x's together, you're going to get x to the r. Similarly, here we're going to get 2x times y prime, which is k times r times x to the r minus 1. Plus finally, or sorry, minus 6 times our y, which is k times x to the r. So if we simplify these all down a little bit, all of the variables should just be x to the r. X squared times x to the r minus 2 is x to the r. X times x to the r minus 1 is x to the r. So we can kind of just focus on the coefficient. What we're really going to have here is k times r minus 1 times x to the r plus 2 times k times r times x to the r minus 6 times k times x to the r. And if we want this to equal 0, it means we need the entire coefficient. So if we factor out the x to the r, we're left with k times r minus 1 plus 2 times k times r minus 6 times k. The only way for this to be 0 is for this coefficient to equal 0. And there's a couple ways this could happen. Unexcitingly, it could happen if k was 0. Right? If k is 0, you get a 0 there, a 0 there, and a 0 there. But that's not very exciting because k was 0, your solution is just y equals 0. Not that it's not valid, it's just not interesting. But let's take a look. So either we factor here, we have k times r minus 1 plus 2 times r minus 6 equal to 0. We can either go in the direction of setting k equal to 0, again, not exciting, or setting all that equal to 0. And if we do that, we have r squared minus r plus 2r minus 6 equal to 0, which becomes r squared plus r minus 6 equal to 0, which factors as r plus 3. Sorry, that looks terrible. Factors as r plus 3 times r minus 2 equal to 0. So you could get r equal to -3 or r equal to 2. So there's a few different solutions for y equal to k times x to the r. You could either have y equal to 0 if k is 0, or y equal to some k times x squared, or y equal to k times x to the -3rd. These would all be general solutions to this particular differential equation. We were told what they looked like, and we were told they looked like y equals kx to the r, and then we just determined either k had to be 0 or r was 2 or -3. So a little, maybe that's a little different than what we've seen in the past. Not an unreasonable thing to ask, but probably a little bit harder. Hard is not the right word, just a little different, right? We haven't seen this, so a little different than what you might have seen. And then the thing you're most likely to get asked is to just solve a differential equation. So someone could easily ask you to solve something like dy dx equal to y squared plus x squared y squared. Sorry, I have to remind me. Do we know that the derivative of the arctangent is?
Should.
No, I'm really asking, like, is that something that you have learned?
In this class.
Okay, but in the previous class? Okay,
But not.
okay. Well, we'll look at this one and then let me just point this one out. So if we were trying to do this, solve this differential equation, can we separate those variables on the right hand side? We can. So if you've got dy dx all by itself, if you can factor the other side into just x's and just y's, it is definitely something you can separate. So I could see definitely asking, like, can you separate this? And like, oh yeah, we can. We can write it as y squared times 1 plus x squared. Oh, actually, sorry, we're not even gonna need arctangent. Never mind. I've got things back, not backwards, just, yeah. If I had my variables the other way, that was different. So here, we're gonna separate. We're gonna get 1 over y squared times dy equal to 1 plus x squared dx. And then we're gonna integrate both sides. 1 over y squared is y to the negative second. If we integrate that, we're gonna get y to the negative first divided by -1. Anti-differentiating the other side, you get x plus x cubed over 3 plus c. Then we're going to solve for y. If we can, right? Sometimes you might have a differential equation where you can't actually solve for y. But most of the time, if you're being asked it, you will be able to. Multiply both sides by -1. Got y to the -1 equal to negative x minus x cubed over 3. And I would actually write minus c here, just because I've noticed that Dr. Burke seems to, whenever she multiplies both sides by a negative, seems to change the constant to a negative c. It really doesn't matter either way, but it'd be safe. And then y to the negative first really means 1 over y. So 1 over y equals negative x minus x cubed over 3 minus c. And you take the reciprocal, the entirety of both sides, and get y equal to 1 over negative x minus x cubed over 3 minus c. And if we weren't given an initial condition, we would stop there. We might stop there. I don't know how much simplification you're expected to do. If someone doesn't like fractions and fractions, you might have to multiply the top and bottom by 3 and write this as y equal to 3 over negative 3x minus x cubed minus 3 times c. Just because sometimes fractions and fractions are considered unsimplified. But I would probably leave it like this because it seems like it's getting at the point. Let's look at another one. Yeah, question.
You do one with use of.
Say that one more time.
You do one with use of.
Yes, definitely. So. Yeah, sure. Let's say we have. Sorry, one sec. Yeah, let's say we have the following. We have y prime plus 2x times y. Sure. Equal to x. Yeah, that's probably not super exciting, but that's fine. Okay, so this one's certainly written in a way that's implying we should do what? Separate or first order linear? I would, well, so you're right that we can separate. I would say it's written in a way that's encouraging you to use first order linear with an integrating factor. Because it's written as y prime plus a function of x times y equal to a function of x. But let's actually talk about the fact that you can do this either way. Now, it might not be a use of problem if we do it the other way. But let's take a look. We'll do a use of if it's not this one. So if we wanted to separate instead, we would isolate y prime and write it as x minus 2x times y. And then on the right hand side, we'd factor out an x, and you have a 1 minus 2y over. And yeah, most of the time it's probably easier to separate. So if you were given this and weren't told which way to do it, a lot of the times we would separate. So occasionally, sometimes it really depends. Like sometimes it's better to do one way versus the other. So here we're going to have dy dx equal to x times 1 minus 2y. So 1 over 1 minus 2y dy is equal to x dx. And if we integrate both sides, we have the integral of 1 over 1 minus 2y dy equal to x times dx. And before we get too much further, let's say that we also have an initial condition, just so I can say I'm not just adding it at the end. Let's say we're also given the initial condition that y of 0 is equal to negative 6. Okay, so now if we integrate both sides, so we could do a u sub here. You can kind of get it without doing a u sub, but we could also say, well, I'm going to let u equal 1 minus 2y. My du is negative 2 dy. So I have negative 1/2 du equal to dy. So then we're going to have the integral of 1 over u, and my dy is going to be -1/2 du. We integrate that, we get -1/2 natural log of the absolute value of u. And then that becomes -1/2 natural log of the absolute value of 1 minus 2y. But I also think you can totally get away doing that and just saying, we know that if you've got 1 over something linear like that, you're going to get the natural log of the absolute value of 1 minus 2y, and then you're dividing by the coefficient of your variable. So sometimes people do that as kind of a shortcut. And say, I don't really need to do the u sub here if it's just a linear function of my variable. Just like we've talked about how if you're going to do like the integral of, sorry, this is a quick aside here, like the integral of e to the 6x, sure, you could do a u sub, or you could just say it's e to the 6x divided by 6. Because you know, when you take the derivative, you're going to multiply by 6 because of the chain rule. You look like you have a question, which is fine. But if you don't ask them, they are.
For the, so I'm just confused how you go from the -1/2 du dy to the part below it.
Sure. So when we're doing a u sub, what we're really doing is we're rewriting the integral in terms of new variables. So I'm taking this integral, the integral of 1 over 1 minus 2y times dy, and I'm rewriting in terms of u. And so whenever you're doing a u sub, it is vital that you first make sure that dy turns into whatever it's equal to in terms of du. So what I did with there was I said, oh, this dy is getting replaced by the -1/2 times du. And we usually pull the constants out in front because it's a pretty standard thing to do. And then the rest of it, the 1 over 1 minus 2y, well, the 1 minus 2y is what we said u is equal to. So that's where our u is right there. So what we're doing is we're just taking this integral and writing in terms of the new variable u.
Shortcut, you get -1/2 and you get, because you're multiplying it by the derivative of what's inside of the parentheses. But that is still, because you get -2, you still have that with the 1.
You mean like right here?
Well, the shortcut.
Here,
Yes.
yeah. So I'm really thinking this is the natural log of the outside of 1 minus 2y
Yes.
divided by -2. I'm just writing it as times -1/2.
But the -2 is
From the coefficient of the y.
Yeah.
And here's why. If we took the derivative of the natural log of 1 minus 2y, what would we get? Well, the derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff is 1 over stuff, but then what do you have to multiply by?
what's inside.
The what of what's inside of it. The derivative. Oh, look, there's a -2 there that we didn't want. So that's why we need a -1/2 out in front, so that when you do the derivative, it'll cancel out. So that the derivative of this -1/2 times the natural log of 1 minus 2y is equal to just 1 over 1 minus 2y. That's why we're dividing by that -2 there. Seem good? It's kind of the same reason, like if I said the antiderivative of cosine of 7x, well, it's not just sine of 7x, because what's the derivative of sine of 7x? It's cosine of 7x times 7. So I need a 1/7 to balance out and make sure that the derivative comes out correctly. And that's a very common thing that happens when you have a u sub where your u would have just been like a linear function of x, meaning some mx plus b, like 7x or 2x plus 5. That almost always happens. Sorry, we've kind of gotten a little bit all over the place here. So we have now our antiderivative, which is -1/2 the natural log of 1 minus 2y, and I am dropping the absolute values because we can do that, it'll work out. Equal to our integral of x, which we hadn't done yet, which is going to be x squared over 2 plus c. So whenever we're solving something like this, I would always recommend going at least until you get to the part where you've got y kind of not inside the logarithm anymore. Here's what I mean. Let's multiply both sides by -2. So the natural log of 1 minus 2y is going to be -2 times x squared over 2 minus 2 times c. That -2 times x squared over 2 is just negative x squared. And then you're going to have e to the natural log of 1 minus 2y equal to e to the negative x squared minus 2c.
Oh, why can we say the absolute value goes away?
Well, so okay. So let's keep it for a second, and I'll show you why. So let's pretend like we still got it. And here's what's gonna happen. Right now, we break this apart, it's e to the negative x squared times e to the negative 2c. But e to the negative 2c, well, so sorry, let me one more line. Absolute value of 1 minus 2y is equal to e to the negative 2c times e to the negative x squared. And then we can say, and here's where it happens, that 1 minus 2y, drop the absolute value. Well, if the absolute value of this is equal to all that, it means the insides were either all of that or the negative of all of that. Had to be one of the two. And so then what we can say is, well, whatever needs to be here, this constant, we're just going to call a. So what we're really going to say is 1 minus 2y equals a times e to the negative x squared. And the thing is, we didn't really need the absolute values the whole way to do that, right? If we had said at this juncture here that we just had 1 minus 2y equal to e to the negative 2c times e to the negative x squared, we could have just pretended like, well, we really have 1 minus 2y equal to a times e to the negative x squared, and ended up at the same place. It's also totally fine to keep them. It's just, it's perfectly okay to drop them as long as we understand what we're doing. And then we can plug in x equal to 0 and y equal to -6 to figure out what that a is going to be. So if x is 0, you're going to get a e to the 0 on the right. And if y is -6, we're going to get 1 plus 12 on the left. So it looks like a is going to be 13. And we're going to go back this way and say, okay, 1 minus 2y equals 13 e to the negative x squared, and then actually finish solving for y. Sometimes it's okay to solve for c before you finish solving for y. It's actually always okay, but sometimes there's like a moment where it's like, oh, this looks good. So then I would probably say 1 minus 13 e to the negative x squared equals 2y, and then divide both sides by 2 to get y equal to 1 minus 13 e to the negative x squared divided by 2. Yeah, that's important. I will point out, obviously, I haven't talked about partial derivatives today. I know you talked about that in class today, but I figured it's documenting your midterm. You guys probably would want to rather talk about midterm stuff. So the plan for Wednesday is also to kind of do a review. We'll probably talk more about the graphing stuff and maybe some more problems. I figured today we can talk about differential equations, and Wednesday we can talk about the other stuff or whatever you want to talk about. That's one other thing I wanted to say. Or potentially whatever practice exam I've done, although I will also post solutions to that. So if we don't cover it in class, it should be okay. But let's look at, yeah, sure. Let's look at that. That's a fine question. So say we had the following differential equation. Then we have x squared times y prime plus 2xy equal to two x. And I was trying to change up this problem to make it more confusing. I think I actually changed it up in a way that makes it easier. That's all right. Sometimes that's life. So I will point out this does look like a first order linear differential equation. So the first thing we need to do is to make sure that we can write it so that y prime is all by itself. So since this is a first order linear differential equation, I'm going to divide everything by whatever is multiplying y prime. So we're going to rewrite it as x squared y prime divided by x squared plus 2xy divided by x squared equal to 2x divided by x squared. Yeah, I do think I exactly wrote this in the way that makes it the way it should have looked in the beginning, just fine. So then simplifying, we have y prime plus 2 over x times y equal to 2 over x. And I don't know specifically if Dr. Burke has said what kind of work she wants you to show for solving a first order linear differential equation. I don't imagine she wants you to jump straight to the end. Like, I think she wants you to, well, actually, do you all know, has she said what she wants you to do for problems like this?
See, we just do all the work.
Okay, so I guess the question I have has she said she's okay with you just saying, I know the integrating factor is gonna be,
Going through the integrating factor?
sure. Well, so if I were doing this the way I was used to doing as a student, at this point, I would say, oh, I know the integrating factor is supposed to be e to the integral of 2 over x. That's where my brain goes next, but I feel like you're saying we do something different, which I know.
I know the integrator.
So what I think Dr. Burke has been doing is saying, oh yeah, we know that this side needs to be, we multiply everything by the integrating factor. So we have I times y prime plus I times 2 over x times y equal to I times 2 over x. And then we're supposed to observe that, oh yes, we know that this side is supposed to be the derivative of the product of I times y. So this is exactly the derivative of y times I. Which means that, well, when you take the derivative of this product, you get y prime times I plus I times, I prime times y, which means that I prime has to equal I times 2 over x. So if we set that up, I will say this feels like a very different, I like doing it this way. It just feels very different than what I'm used to doing. So we set that up, we have that I prime equals I times 2 over x. Or written another way, di dx equals I times 2 over x, or 1 over I di equals 2 over x dx. Does that seem more like what you, yeah, okay. So we integrate both sides. The integral of 1 over I is the natural log of I. The integral of 2 over x is 2 times the natural log of x. We have to be careful here. I need to solve for I. What's I equal to? There's a couple ways you get there. You could just say e to the natural log of I equals e to the 2 natural log of x. I think the easier way to go here is just to say that this is equal to the natural log of x squared, because that 2 gets to come up. And then you can just say that I is equal to x squared. That's our integrating factor.
Plus C.
No, when you're dealing with the integrating factor part, no plus c's, no absolute values. And this is kind of why I was laughing at myself in the beginning, because the integrating factor is exactly the thing and dividing everything by in the first place. So when we multiply everything back through by I squared, we're just getting back to the original equation we started with. So I'll point out, right, if we write this as x squared times y prime plus 2x times y, oh yeah, that's exactly the derivative of x squared times y. Because it's x squared times y prime plus 2x times y, product rule, equals x squared times 2 over x, which is just 2x. So it feels like we kind of do a whole lot of work for kind of nothing. Not really nothing, because you had to do this work to know what you had in the first place. But still, it kind of, it always feels like, oh, I'm just getting back to the thing I started with. That feels a little silly. But now we know what we've got. We know that we have that the derivative of x squared times y is equal to 2x. And then we can anti-differentiate both sides. We can say that x squared times y is equal to the antiderivative of 2x. And this is where we do absolutely have to have a plus c after we anti-differentiate. So we're going to say that x squared times y is equal to x squared plus c. And that c has to get divided by whatever we divide both sides by. So then we're going to solve, and we're going to say that y is equal to x squared divided by x squared plus c divided by x squared, or probably written in a more typical way as y equal to 1 plus c over x squared. That's our general solution, but we also had an initial condition. So then if we use the fact that y of 1 is equal to 2, we can say, okay, well, great. I'm going to plug in 2 for y, 1 for x, and then we end up getting c also equal to 1, because 2 minus 1 is equal to c. C equals 1. And please do yourselves a favor. Don't stop here, right? It would probably be enough work to get almost all the credit, but really, if you're asked to find the particular solution with an initial condition, we then need to go and say, oh, we're going to put those two things together and write that our actual solution is y equal to 1 plus 1 over x squared. Let's look at one more, because I got a couple minutes. So let's say we had this setup. I know, let's say one more thing. So let's say we were given the xy prime plus x plus 1 y equal to x e to the 2x. And what if we were just asked to find I of x? So I would still start by writing it in the standard way, dividing everything by x. So I'm going to rewrite this as y prime plus x plus 1 over x times y equal to x e to the 2x divided by x is just e to the 2x. Oh, I forgot my prime there. And if we're doing it the way Dr. Berg likes it, which again, I think is good, we're going to say that I times y prime plus I times x plus 1 over x times y is equal to I times e to the 2x. And then we know that this side is supposed to be I times y prime plus I prime times y. So we do all that to figure out that, oh, okay, we need the derivative of I to be equal to I times x plus 1 over x. And then we would separate. So this is di dx over on the left equal to I times x plus 1 over x on the right. And then I'm going to rewrite this as 1 over I di equal to x plus 1 over x dx. And now this looks like it might be terrible. It's actually not. What's the antiderivative of 1 over I? Okay. And usually there'd be an absolute value, but when it's an integrating factor, we totally just ignore the absolute value. And now this x plus 1 over x looks terrible, but it's not, because you really just have x divided by x, which is 1, plus 1 divided by x. And we can certainly integrate that. The integral of 1 is x. The integral of 1 over x is the natural log of x. And then if we want to solve for I, we're going to say that e to the natural log of I is equal to e to the x plus natural log of x. And for me, I would do two things. Right, exactly. The left-hand side certainly should be I. The right-hand side, we should write as e to the x times e to the natural log of x, and then e to the natural log of x is just x. So our integrating factor here is x e to the x.